Hello, everyone. This is Sye. Thanks a lot, Todd. Um, and thanks, everyone, for joining in today. So today's Tech Talk is computing seismic load using dynamic analysis. In today's discussion, we will focus on the various dynamic analysis methods with specific references to the ASCE 710 code. The code permits engineers to carry out seismic analysis using one of the three methods, namely the equivalent lateral force procedure as outlined in section 12.8, the modal response spectrum analysis method as outlined in section 12.9, and the response history procedure as outlined in chapter 16. Now, out of the three methods, the first one is a static method, whereas the second and the third are the dynamic ones. Now, out of the three, the equivalent lateral force procedure is possibly the most widely used by practicing engineers, mainly because of its simplicity. The fact that it's a static analysis means it is easier for us to do hand calculations if required for quick verification, and results are also much easier to comprehend. However, one thing to keep in mind is that although equivalent lateral force procedure is a simple analysis method, it is not universally applicable under all scenarios, and we will discuss that more in our next slide. This table 12.6-1 from ASCE 710 provides guidelines on the applicability of these three methods. The P's in this table indicate that particular analysis type is permitted, whereas an NP means the analysis type is not permitted. The table essentially refers to certain terms like seismic design categories and risk categories. And before we dive into the details of this table, let us spare a moment to understand what these items are. Starting with the risk category, it refers to the level of risk the structure poses to human life in the event of its failure. And it depends on what the building is being used for. So higher the risk to human life caused by its failure, higher is the risk category. The details are provided in this table 1.5-1. Next is the seismic design category. Structures shall be assigned an appropriate seismic design category as outlined in these two tables. These are from ASCE 710. And as you can see, it depends on the risk category and the spectral design response acceleration parameters, SS and SDS and SD1. If the seismic design category comes out to be different based on these two tables, we need to choose the more severe one. So now that we have talked about the risk category and the seismic design category, let me just go back to the table 12.6-1. And in a nutshell, this table tells us that for any structure in seismic design categories B and C, one can use pretty much any of the three methods that we talked about. For seismic design categories D, E, and F, these methods, like all of these methods, are permitted under certain condition. For example, it has to belong to a low risk category. It cannot exceed a certain number of stories or a certain structural height, and should not have certain horizontal and vertical structural irregularities. So any structure that does not satisfy the conditions marked within this red block warrant the use of dynamic analysis. Hence, the first thing that you need to ensure as an engineer is that you are choosing the right seismic analysis procedure for the structure you are trying to analyze. Having said that, it is important to mention that you have to carry out the seismic analysis as per the equivalent lateral force procedure anyway, even if you are using one of the dynamic analysis methods, because the code asks you to compare the base shears from a dynamic analysis with that from a static analysis. And in case there is a significant difference between the two, the dynamic analysis results has to be scaled up. And we are going to talk more about this later in this tech talk. Now, besides choosing the right analysis method, it's also important that we prepare the right type of structural model for our analysis. More specifically, whether a simple 2D frame analysis is good, or whether we need to prepare a 3D model. The ASCE 710 section 12.7.3 lays out some of the ground rules for deciding on that. The first thing it says is the model should adequately represent the spatial distribution of mass and stiffness. Whereas a 2D model may be used for analysis, but when a structure has certain types of horizontal structural irregularities, as outlined in the slide, having a 3D model is essential. These horizontal irregularity types are all detailed out in table 12.3-1. Type A and 1B refer to torsional and extreme torsional irregularity. Type 4 is basically an out-of-plane offset irregularity when at least one of the lateral force resisting elements is offset in plan, leading to discontinuity in the flow of the lateral force through the structure. And type 5 refers to lateral force resisting systems not being parallel to the major orthogonal axis. So once we have decided on the analysis method to use and what type of model to use, next important thing to figure out is what type of lateral framing system to use. Table 12.2-1 of the ASCE 7 lists the different types of lateral force resisting systems that a structure may have, along with the associated design coefficients for each type. Knowing these coefficients is important because no matter whether you are using a static analysis or a dynamic analysis, these are directly used as inputs for calculation of the design base shear. The table also imposes some limits on using certain seismic force resisting systems within certain design categories. So for example, as seen in this slide, one can use special reinforced concrete shear walls in seismic design categories D and E only if the structure height is less than 160 feet. Similarly, if the seismic design category is between D through F, the ordinary reinforced concrete shear walls are not permitted to be used. So you should choose an appropriate lateral force resisting system for your structure based on the seismic design category and the structure geometry. You are allowed to use a different type of lateral framing system in each orthogonal direction. You can even use a combination of lateral force resisting systems, commonly referred to as dual systems, in a single direction. And there are a lot of useful guidelines that the ASCE 7 provides on that in section 12.2. Let's now discuss some more specifics related to dynamic analysis. Natural frequencies and mode shapes are the basic parameters that shape a structure's response to a dynamic loading. So a first step to carrying out any kind of dynamic analysis is to solve for the frequencies and the mode shapes using the equations shown here. The free vibration problem is solved to extract these frequency and mode shape values represented as omega and q in this equation. Since there is no external force involved, the right side of the equation becomes 0. As you can see from the equation, the mode shapes and frequencies are direct functions of the structure's mass and stiffness. Results of the eigensolution can vary significantly depending on how the mass and stiffness are modeled, and this can have direct impact on the results of a dynamic analysis. Hence, it's vitally important that proper care is taken in mass modeling and stiffness modeling. Talking about mass modeling, a question that we frequently run into at technical support is what loads should be included for mass modeling. The ASCE 7 section 12.7.2 offers some guidelines in this area, which I have listed in this slide. It basically says that all loads above the base of the structure needs to be included. In areas used for storage, a minimum of 25% of the live load has to be included. There are some exceptions. Where partitions are required to be provided, one has to include the actual partition weight or a 10 pounds per square feet floor load over the entire floor, whichever is greater. Weight of any equipment sitting on the structure above the base, where your flat roof snow load exceeds 30 pounds per square feet, the code asks you to consider 20% of that, irrespective of the slope of the roof. Weight of any landscaping or any other material at roof or any other level. Now, how to include the masses in the analysis? Different software have different ways of modeling the masses. In STAD Pro, and I'm going to focus mainly on STAD Pro in our Tech Talk today. In STAD Pro, the masses are modeled as loads. So to model all the items that we discussed about in our previous slides, we can use a combination of like self-weight load, nodal load, member load, floor load, etc. The software then internally converts these masses, these two masses, by dividing these loads by the acceleration due to gravity. A very important aspect of mass modeling is that you need to apply these loads in all possible directions. For example, even if it is just a dead load acting in the vertical direction, when it comes to mass modeling, the only way to tell the software that the mass can vibrate in all three directions is to apply the load in all three directions. The load should also be entered as a positive number, even though it may be acting in the negative y direction, because eventually the software is going to calculate the masses from these loads. And STAD Pro does an algebraic summation of masses at the various nodes. And so if some are entered as positive numbers and some are entered as negative numbers, these masses may cancel out. So be mindful of that. Coming to stiffness modeling, stiffness matrix is created by the software internally, taking into account the cross-sectional property, the material, supports, releases that you enter as part of the modeling process. One should also take proper care in modeling any lateral force resisting elements like braces, shear walls, and moment frames. Modeling of diaphragms is also very important from dynamic analysis and lateral load analysis standpoint. Rigid diaphragms may be modeled using float diaphragm option in STAD Pro. This ensures that the torsional effect due to the eccentricity between the center of mass and the center of rigidity is accounted for in the analysis. If you have flexible diaphragms, you should also go ahead and model it using a mesh of plates. So once the mass and the stiffness are modeled and the modal analysis is carried out, the first and foremost thing to ensure is that enough number of modes are considered in the dynamic analysis so that the cumulative mass participation in each direction of interest is at least 90%. This requirement is outlined in section 12.9.1 of the ASCE 7 code. In STAD Pro, by default, 6 modes are considered, but that may not be good enough for all types of structures. So you can find out the mass participation from the analysis output file as shown in this slide, and depending on the participation amount, you may need to consider additional modes over and above the 6 modes. And this can be achieved through using the cutoff mode shape command that allows you to tell the software how many modes to consider. At this point, let me bring up the StatPro software and show you a couple of things that we discussed about. So this is a 3D model, and just let me do a 3D rendering of the model. So as you can see, it's a simple steel structure, spatial moment resistant frame in this case with a reentrant corner. I have defined a couple of reference loads. So this is basically the dead load where I have included the self weight, and in all the floors at 10 feet, 20 feet, and 30 feet, I've included a 75 pounds per square feet dead load. And the reference load case number 3 is a live load where a 40 pounds per square feet live load is included on all the floors. And this is the mass modeling. So this mass is created by combining the dead load and 25% of the live load. So self weight, as you can see, applied in all directions, and the dead load, that's 75 pounds per square feet, applied again in all directions in all the floors, and 1/4 or 25% of that 40 pounds per square feet, that's the live load part, applied in all directions. So that constitutes my mass modeling. And also, if I just double click on any of these options, you can see the pressure has been specified as a positive value. So this is how you model the mass. And then this is my equivalent lateral force analysis. So although we are going to do a response spectrum analysis in this case, it's essential to also include the static analysis as part of the model. So what we have done here is chosen IBC 2012 as our code. There are a variety of other codes that StatPro supports. And all I have done is chosen the zip code, and the software has automatically figured out the SS and the S1 values. And I have specified a couple of other factors. My structure is in risk category 3, so importance factor of 1.25. It's a spatial moment resistant frame, so the response modification factor has been considered as 8 in both directions, and the site specific coefficients are also entered. The site class is D, and this one actually uses like 100% of the live load, 100% of the dead load, I'm sorry, and 25% of the live load as the seismic weight. So let me quickly go to the output file and show you from where you can check the the eigen solution. So this is this is the result of that solution. This is the result of the equation that we talked about in our presentation. So for each mode, you're going to get the frequencies and the time periods, and this is where you get the mass participation. So you are so you will mostly be interested in this column, the summation of x and summation of z. X and z are the two lateral directions, if you remember, in StatPro. And so the cumulative mass participation, which is indicated in these columns, has to be more than 90%. So this is one check that you need to make and ensure that you consider enough number of modes so that you get enough participation. Going back to our presentation, in a response spectrum analysis, the structural responses are calculated for each mode, and then this modal responses are combined using a combination method. ASCE 712.9.3 talks about the various combination methods. StatPro supports all of these and many additional ones, as shown on this slide. CQC is the default method of combination and is preferred over the SRSS, especially when there are a number of closely spaced modes. The ASCE provides guidelines on generation of design response spectrum in section 11.4.5 of the code. In absence of site-specific response spectrum data, one can make use of this. The equations on the right-hand side define each section of the spectrum. This response spectrum generation is automated in StatPro. One just needs to choose the IBC 2012 ASCE 710 as the seismic code, and the software would be able to generate the design response spectrum based on the code. Alternately, if there is a site-specific response spectrum data available, then one can just choose the custom option for the code and then define the period versus acceleration data directly into the software. The response spectrum data is defined earlier, may be scaled under certain circumstances. For example, if the spectrum is in terms of acceleration due to gravity, as opposed to being specified in units of acceleration, then you'd have to scale it by the G value. In addition, the ASCE 7 section 12.9.2 mentions that the spectrum generated based on the code should be divided by the quantity R by IE. So this too can be entered as a scale factor when defining the spectrum data in the software. One also needs to be mindful of the fact that for displacement and drift calculations, the results need to be multiplied by the factor CD by IE. So for our model, the scale factor is calculated as IE by R. IE is the importance factor of 1.25 and R is the response modification coefficient. So the factor comes out to be 0.156, and it's applied through the direction factor. Let's now go back to the model and see how these things are defined. So earlier I was within the load case definitions, or this definitions box, definitions tree. Now I go to the load case details, and this is my response spectrum load case. So here is where I choose the code. Here is where I choose the combination method, which is CQC. The save option allows me to save all the joint accelerations in a file. And these are the site-specific coefficients, the site class, and again, I have just specified the zip code out here, and the software has picked up the SS and the S1 values, and based on that, it has come up with this period versus acceleration values as per the ASCE 710 code. And this is where I specify the scaling for the spectra. And we calculated this value as 0.156, so I'm applying the scale factor in here. Now, you will note that there is another scale option out here, which is grayed out. That's because we have chosen the code as IBC 2012, in which case the software directly calculates the acceleration in terms of acceleration units and not in terms of G. So just to safeguard against any user mistake, well, we have grayed out this option, but you can put in your scale in here. And in case you have a site-specific spectra, you can always choose the custom option, and in that case, this will be active. But you'll be required to key in the period versus acceleration data in this table. Okay, so that's what's in this table. Let me go back to our presentation for a second. Now, scaling of the results. Although the ASCE may require you to carry out seismic analysis using a response spectrum analysis, but the section 12.9.4 mentions that you need to carry out an analysis as per the equivalent lateral force procedure as well. And in case the modal base shear is less than 85% of the base shear obtained using the equivalent lateral force procedure, the response spectrum results would have to be factored by the amount highlighted in this slide. So basically for our model, the equivalent lateral force procedure base shear comes out to be 71.13. We'll take a look at it soon. And response spectrum base shear comes out to be a little over 60. So the ratio comes out to be just greater than 85% in one direction and equal to 85% for the other direction. So no further scaling of the results is required for this particular model. Scaling of the drifts. For getting the scale factors for the drift calculations, there are two sections, section 12.8.6 and section 12.9.4.2, which are shown in this slide. The section 12.8.6 is applicable for all types of analysis, static or dynamic, whereas the 12.9.4.2 is specifically meant for dynamic analysis. Now, as far as the 12.9.4.2 is concerned, just be aware that the static base shear that you are checking against is computed as per equation 12.8-6, which is basically a lower limit on the computed static base shear. So this is not the actual static base shear, but a certain minimum value of it. And only if the dynamic base shear is less than 85% of that lower limit, you need to scale down the results. Rather, you need to scale up the results from the dynamic analysis with the factor indicated. Else, this second scaling is not required. So again, coming to our model, the first scale factor comes out to be 4.4, and while we look at the second clause, we see that the response spectrum base shear is much more than the minimum value of the static base shear, so we are good on that. And we are going to create a set of load cases for the drift checking, and this factor 4.4 will be applied on those cases. So those will be cases 300 to 307 in our analysis model, as we will see in a minute. And this table shows where you are going to get the allowable value of the drifts. So for a risk category of 3, the value is 0.02 times the story height, and this is entered as that allowable drift factor, as you can see from this slide. So let me go back to the model and show you how these things are implemented. First, let me show you the base shear calculation for the static analysis. So this is where that 71 kips comes from. And then if you go here, you'll see the base shear reported from the dynamic analysis. And we are considering CQC, so we'll go by this 60.73 value. And then we have defined a number of load cases 300 to 307, where these are specifically for the drift check, where we have used the factor of 4.4. So each of these cases have been factored with 4.4. And this huge values of moments are because the diagram is not scaled. So let me just scale it down a bit. Okay. So just to give you an idea as to how to set this check up. So for the drift calculation, these are the cases 300 to 307. In each case, I factored the loads by 4.4, and then I have used a load list 300 to 307, and then asked the software to do a drift check based on only these load cases. So just be aware of that, and that 0.02 is that allowable drift factor. And let me also show you how the results are listed. So if I go to the analysis output file, go to the results, story drift, there you can see the results of your drift check. At each story, 10 feet, 20 feet, 30 feet, the software prints out the drift amounts, and then it also tells you whether it's a pass or a fail, depending on the allowable value that you specified. So going back to the presentation, Regarding distribution of the horizontal shear, the section 12.9.5 refers to section 12.8.4, which mentions that seismic story shear shall be distributed to the vertical elements of the lateral force resisting system based on the relative stiffness of the vertical resisting elements and the diaphragm. Inherent torsion is automatically accounted for in the analysis when rigid diaphragm is modeled. And for response spectrum type loading, the accidental torsion can also be accounted for in the load definition itself, and we'll see that in a moment. Also, as seen in the slide, section 12.9.5 mentions that amplification of the accidental torsion is not required when accidental torsion is included as part of the dynamic analysis model. So going back to our model, let me just again bring back that response spectrum load input. And now we are going to focus on this part. See, we have turned the use torsion option on, and we have defined rigid diaphragm at all the floor levels. So this option, dynamic eccentricity, would ensure that the torsion due to eccentricity between the center of mass and center of rigidity is accounted for, whereas this option accounts for the accidental torsion. Going back to our presentation, P delta effects. One of the challenges that practicing engineers are confronted with is to account for P delta effects even when carrying out a dynamic analysis like response spectrum. The challenge stems from the fact that response spectrum results are all absolute values, using which one cannot really carry out a second order analysis like a P delta. Moreover, these values of these responses are not at the same instant of time, which makes carrying out a second order analysis with these values kind of meaningless. So before we dive into how to resolve the issue, let's first look at the at what the code says in section 12.8.7. It says that P delta effects can be neglected when the stability coefficient using the equation 12.8-16 is less than 0.1. It also provides an upper limit for this stability coefficient as outlined in section 12.8-17. So if theta exceeds theta max, then the structure is potentially unstable and it has to be redesigned. But for situations where theta is greater than 0.1 but lesser than theta max, one is allowed to account for the P delta effects by multiplying the displacements and the member forces from the first order analysis by a factor of 1 by 1 minus theta, in lieu of carrying out an actual P delta analysis. So I think this is a much better way and easier way to account for the P delta effects when it comes to the dynamic load cases. So coming to our model, at all the levels of the structure, we have calculated the theta and also calculated the theta max. In this case, theta is less than 0.1 and also less than theta max. So no P delta effect needs to be included for this example. However, just to demonstrate how to set up the model with the P delta analysis, I have included it in this particular model. So here is how we calculate the load factor to be used for the dynamic cases to ensure that P delta effects are included. Considering the largest value of theta, which is 0.0073, the factor 1 by 1 minus theta comes out to be 1.007. And as we can see in this slide, all the load combinations, which includes the dynamic cases, have been multiplied by that 1.007 factor to ensure that we comply with the code requirement of including the P delta effect. Now, just to reiterate, for situations where you have to account for P delta effects in your analysis, what you can do is for all load cases except the dynamic ones, you can carry out a P delta analysis. And for the dynamic analysis cases, do a first order analysis, create the associated load combinations, and then multiply the results of those combinations by this 1/1 minus theta factor. And you should be in compliance with the code requirements. So let me go back to the model and explain how the p-delta analysis is set up for all these cases, except the dynamic, and how a first order analysis is set up for the response spectrum case. So in our model, let me quickly bring up the editor, and so starting from load case 5, which is the dead load and live load, and all the combinations, which does for all the repeat load cases, I'm using a p-delta analysis. So you can pretty much include any load case in this block, which does not include a dynamic load case like a response spectrum or a time history. So if it's an equivalent static seismic load analysis, that can be a part of this block. So have all of your repeat loads in here that comprise of the different combinations, except your dynamic analysis load cases. And then you define a p-delta analysis command, follow it up with a change command. After that, you define your dynamic cases. So your seismic case defined using response spectrum in the various directions. And then you follow it up with load combinations where you are combining the gravity loads with this dynamic load case. This is a load combination, remember. And you are factoring those combinations by that 1/1 minus theta factor, so that you are in compliance with the code as far as p-delta effects are concerned. And then these, of course, are my drift check load cases. These are separated. And then at the end, we have the perform analysis, which is basically the first order analysis. So this is how you need to set up the model. All load cases except dynamic, followed by p-delta. Then you specify the dynamic cases, followed by the load combinations, drift combinations, and then the first order analysis command. So let me go back to the presentation. Talking of some of the outputs that you can get from the response spectrum analysis, the masses are listed in a mass.txt file. This is an ASCII file that is created in the same folder as your StatPro model. Similarly, you can look at the nodal accelerations in a .acc file. That's also is created as part of the folder where your stat model is. The x1, x2, x3 represents the translational accelerations at the nodes, and x4, x5, x6 correspond to the rotational accelerations of the joint at the various joints in radian per second square. You can get the accelerations for each mode reported in the analysis output file. Software also provides you the dynamic weight by accounting for all the seismic weights or seismic masses. The total weight that is captured through the various modes is reported as the modal weight, and any weight that could not be captured through the modes is reported as the missing weight, which in this case is negligible, indicating that the dynamic response of the structure has been pretty well captured by the modes that we have considered. Amongst the other outputs, you can, of course, get the base shear, as we have seen in the analysis output file. And it also reports the story shears at the various story levels. So finally, the load combinations, just be mindful of the fact that seismic force is reversible. So always ensure that you create a set of load combinations where seismic load is added to the other loads in one set, and in the other set, ensure that it's subtracted from the other loads. Now moving over to the other form of dynamic analysis, which is response history, also referred to as time history. In this type of analysis, the dynamic force is applied as a time versus force data. This type of analysis is most widely used for analyzing structures under dynamic loads from a vibrating machinery. I've also seen this type of analysis being used for blast analysis. The machine load is represented using a harmonic forcing function. And if it's a blast load, if it's just it's just entered as a random force versus time data. When it comes to seismic analysis, though, the force due to earthquake can be represented as a ground acceleration versus time pairs for the entire duration of the earthquake. Although I must say here that response spectrum is much more widely used compared to time history when it comes to applying seismic loading. What we see here is the basic equation of motion, which is a differential equation where the variables are coupled. The analysis is performed using the modal superposition, where it is assumed that the structural response is obtained from the P lowest modes. The coupled equations are uncoupled and displacements are solved at each time instant. Just as in case of a response spectrum analysis, the mass and stiffness modeling are critical for calculation of the mode shapes and the frequencies which form the basis of the modal superposition. So everything that we have discussed so far related to modeling of the masses and stiffness holds true for the time history analysis as well. The main difference between response spectrum and the time history loading is that for time history, the loading is specified as a time versus acceleration data, whereas for a response spectrum, the loading is entered as a spectral acceleration versus time period data. Similar to how the response spectrum results were scaled, time history results also needs to be scaled as outlined in section 16.1.4 of the ASCE 710 code. On the right side is that specific section of the code, and on the left is a screen grab of the dialog box in Stat Pro where this scale factor is applied. This slide shows the relevant clauses from the ASCE 710 where the code specifies how to scale the forces and the drifts from the time history analysis. And this is very similar to what we have seen for the response spectrum analysis. So for our model, the time history based shear comes out to be about 31.86. The equations 12.8.5, 12.8.6 is checked in order to find out the minimum value of base shear from the static equivalent procedure, and then we find that the base shear from time history analysis is more than these minimum values for the static shears. So we are good, and scaling of the drifts and forces are not required. The distribution of horizontal force is very similar to what we have seen for response spectrum. Inherent torsion is automatically accounted for in the analysis when the rigid diaphragm is modeled, so there is nothing you need to worry about. Just model the rigid diaphragm as part of your model. In Stat Pro for time history type loading, the accidental torsion needs to be defined as an additional load case and then combined with the time history load case. So that is the only slight difference in a way from the response spectrum analysis. Also, as seen in the slide, 16.1.5 mentions that amplification of accidental torsion is not required when accidental torsion is included as part of the dynamic analysis model. Now, regarding the results, you can plot a time history of the displacements, accelerations, or velocity at any node of your structure, as shown in the slide. And then you can also ask the software to give you the result at each and every time instant. So for that, you have to use the save option, and then the software is going to create two files, one with an extension of .tim and another with an extension of .frc. TIM file would contain the nodal displacements at each instant of time, and the FRC file would contain the beam end forces and the support reactions at each time instant. These files again are stored in the same folder as the StatPro model, and these are ASCII files, and you can open it using Notepad or Wattpad. Let me quickly go back to our model and show you show you how the time history is set up. For this, I'm going to just close out of this model and open up a time history model. I have actually used the exact same structure, but created a different file just to ensure that response spectrum and time history are specified in separate files. And when you look at these examples, you have a clear file for each case. So time history definition, it's an acceleration time history. It was normalized, so we scaled it up by the G value of 32.2 feet per second square. The data is read from an external text file, eqdata.txt. So this file contains the acceleration in terms of G versus the time. Arrival time, it's only relevant when you have multiple time history loads, and they are arriving at a certain time difference with respect to each other. Like say one may start at say 1 second, another may start at say maybe 3 seconds. So that is when the arrival time kicks in. In this case, it's not used because we just have a ground acceleration starting at time 0. This is where you specify the damping, and this is the acceleration time history. If I double click here, you'll see it's specified as a ground motion in the x direction, and the force amplification factor is 0.156 as we've seen. And then we go to accidental torsion, and this is how the accidental torsion has been applied. So at each level it's calculated and it's applied as a force couple. And then the 50, which is the lateral load, and then accidental torsion, these are combined in these two combinations. So 600 and 601 are basically your load combinations involving the lateral load from time history and the accidental torsion. And then we create the load combinations 200 to 203, where your time history load is combined with the other gravity loads. And similarly, we can apply factors like these scaling factors of 1.007 as we have seen in our slides. So this is how to set up the time history. And just to talk about the output a bit, you can go to this analysis output file, and so this is again the mass participation, and this is where the base shear is listed for the time history, and you get the maximum response at 2.54 seconds. Regarding the graphics, the graphical output, you can go to the post-processing mode, and all of these values that you see here are the maximum responses out of all the time instants. So everything, all of these displacements are the maximum value at any point, considering the entire duration of the earthquake. Similarly, for the reactions and beam results, you can take a look at the displacement time history. So all you need to do is just pick a node, and it will show you how the displacement is varying at that node. And similarly, if you go to layout, you can choose acceleration, and since the node is already selected, it will plot the acceleration at that node for the entire duration of the earthquake. You can just right click, choose save data in a text file, and that would allow you to save the data in an ASCII file. So that's pretty much what I wanted to share with you today regarding the dynamic analysis. And now let me move to the Q&A. So so feel free to type your questions in, and I'll be more than happy to answer your questions. The first question that I have here is, can I not use equivalent lateral force procedure for seismic load generation as opposed to using dynamic analysis? Yeah, definitely you can use equivalent lateral force procedure in lieu of dynamic analysis, but just ensure that you first refer to the ASCE 7 code. The code outlines where you can use equivalent lateral force procedure and where you cannot use. So just ensure that you satisfy that requirement, and then you can of course do an equivalent lateral force procedure. A second question I have is, wasn't your 25% live load already included in your mass modeling load? Yes. So when I created the mass modeling, I included 25% of the live load and 100% of the dead load. And then when I combined the dynamic load with the dead load and the live load, there we had like the full values of the load. But as far as the computation of dynamic load is concerned, or response spectrum load is concerned, we did consider 25% of the live load. I have a question. Can the STAD model being discussed here in the presentation be sent to the participants? Of course. There are two separate models that I have created, one for time history and another is for response spectrum. You will be able to get hold of both these models and take a look at it. I have a question. Is there any software like STAD that can internally determine the required number of iterations based on the required minimum participation factor in a particular direction? Now, you basically need to ensure that there is enough participation. The software can definitely solve for the number of modes that you ask it to solve for. So you should take a look at the mass participation and take a look at the cumulative mass participation rather, and ensure yourself that 90% or more is being considered. There's one more question. Could I have the STAD input file used here? Of course, yeah. We're going to share this with you. Next question, will the STAD file be distributed? Yes, you will get it. Can we download this file? Of course, you will be able to do that. Did not know, the question is, did not know it will give you story shear with base shear. Yes, it will give you the story shear with the base shear. Just ensure that you use a set command in the file called set print 17. And once you receive the file, you will see that set command right at the top. That actually prints out a few extra things besides the usual output. And so so you can definitely get that story shear reported as part of the analysis output file. Next question is, will I get a PDF of the presentation? Yes, sure. We'll provide you with a PDF and the models used in this presentation. Next is, with loads from modal response spectrum analysis being absolute values, how do you handle foundation design when you don't include the foundation in your model? That's actually a challenge, and of course you have to the challenge is, it's actually less of a challenge if you are designing like isolated footings, because you get the maximum or rather the envelope forces, and you just design based on that. But for pile cap, or rather like for mats, where you need to consider like multiple support points, it's actually a little challenging. And what you can do is, like, since these forces are individual maximums and these are not like corresponding forces at the various supports, what you can do is, like, instead we have the individual, like there's an IMR option, individual modal response cases. You can generate those static cases based on the modes from the dynamic analysis. So you can select certain modes based on which the software can create static load cases. You can use those. But we surely do understand it's a challenge when it comes to like mats which are supporting more than one support points. So the other option would be to use an equivalent lateral force procedure. Next question is, why in response spectrum analysis you don't have load combination of accidental torsion and seismic load? In the response spectrum analysis, you may remember that when I specified the load definition itself involved checking a dialog box called use torsion, and that had the accidental torsion option in it. So as part of the definition itself, the accidental torsion has been included. So that's why I did not need to create a separate load case for the accidental torsion. And just to let you know that STAAD calculates this accidental torsion on a mode by mode basis. So for each mode, it figures out what the torsion is, and it computes the equivalent force couple at every level. And it does a static analysis with those force couple to compute the effect of accidental torsion. And it combines that with the modal results to come up with the final modal result that includes accidental torsion. And then the results from the various modes are combined to give you the result from the response spectrum analysis. So that is all included as part of the load definition itself.